In today's lecture, I'm solving few problems from the Wein's law. You know, Wein's law is the relationship between the maximum frequency, which is denoted by lambda max, Greek letter lambda, is proportional to uh, temperature. Okay, so we can write down the formula in this form: 2.9 into 10 to the power 6 nanometer per Kelvin. Okay, while writing this constant, this unit should be nanometer Kelvin. Okay, divided by temperature. This is the temperature of the protostar. Okay, at what wavelength does a protostar with a temperature of 1100 Kelvin radiate most strongly? This is the temperature given. So in this problem, temperature is given, which is 1100 Kelvin. And our target variable is the wavelength, which is the lambda max is equal to what? Okay, so we already have the relationship, which is lambda max equal to this constant value, nanometer Kelvin divided by temperature. Okay, if we insert value of temperature in this Wein's law, which is uh, lambda max is equal to 2.9 into 10 to the power 6 nanometer Kelvin divided by 1100 Kelvin. Okay, we can cancel this Kelvin and only nanometer will be there, so that it is unit of distance, or you know, uh, lambda, which is the wavelength, is simply the length of one wave. If you simplify this one, just here are two zeros, I can cancel two zeros, four zeros will be there. If you calculate these values, you will get something like 2636.36 nanometer. Okay, so this will be the wavelength of the protostar at which it radiates the radiation. It radiates at 1100 Kelvin. Okay, so now let's go to the another question. If wavelength is given, as we did before, we can calculate the temperature. So right now in this curve, we have to calculate the temperature of an object whose black body curve is as shown in figure below. Okay, so x-axis right here is the wavelength of the radiation emitted by some object, maybe protostar or any objects that radiates a certain frequency. Okay, heat energy. So this is x-axis, this is y-axis, right? Along the x-axis, you can see the wavelength. So if you look at our relationship for Wein's law is lambda max is equal to 2.9 into 10 to the power 6 nanometer Kelvin, right? Divided by temperature, T. So what is the peak wavelength? So this is not a straight line. Straight line. So let me erase this one. And probably it will be something like, just wait a minute. I will draw a line like this, right? So this line matches at 500 nanometer, right? So our lambda max from here, lambda max is something 500, around 500 in nanometer, okay? So nanometer. So our goal is, target variable in this question is temperature, right? calculate the temperature of an object, the blackberry. So temperature is equal to what? So if we rearrange this equation, the temperature T is equal to 2.9 into 10 to the power 6 Newton nanometer, sorry, not a Newton meter, a nanometer Kelvin. Temperature is Kelvin and distance is in nanometer, right? Divided by lambda max. Okay. If I insert these value again, 9 into 10 to the power 6 nanometer Kelvin divided by lambda max is right now 500 nanometer. Okay. So nanometer and nanometer can be cancelled, and these two zeros again I can cancel it like this. And if you calculate this one using calculator, that will be 0.58 uh, into 10 to the power 8. Okay, this is in Kelvin, or we can write down like 5.8 into 10 to the power 7 Kelvin. Okay, so this is the temperature of the object.